Okay, hello everyone, welcome to the Black Hole. I am Shahryar Khan, and today we are here to attend a talk by Dr. Mir Faizal, who is a physicist working in Canada right now. So let me introduce Dr. Mir Faizal. Uh, Dr. Mir Faizal did his master's from the University of Durham in the UK in physics and then did his PhD in physics from the University of York, specializing in quantum gravity. After that, he did postdocs from the University of Durham and also from the University of Oxford. After that, he has been the scientific director of the Canadian Quantum Research Institute, and also he is teaching at the University of British Columbia in Canada. He has published over 174 papers in various journals, including Nature. He has an H index of 41, an I-10 index of 118, and also he is in the top 2% of scientists in the Stanford list. And his work in physics spans a broad range from string theory and loop quantum gravity all the way to condensed matter physics and also astrophysics. So it is an honor for us that he has joined us for this online lecture, and I hope it will be a fascinating talk. Before we start, I encourage you all to please turn your mobiles to silent mode so that there is no disturbance during the talk. And after he will first of all give us a presentation, he will present some slides. And after that, we can have a Q&A session. And during the Q&A session, first raise your hand, and then the mic will be provided to you, and only then ask your question. So let me hand it over to Dr. Mir Faizal. He will first give a presentation, and then we will have the Q&A session. So let's welcome Dr.
So are we live
Faizal
now? Or
Yes.
we have been live already?
Yes, we are live. We are live. You can begin
Okay,
your
great.
presentation.
Yeah, you never told me when we are coming live. Okay, great. So,
Yes, we are live.
So I'll be talking basically about physics beyond space and time, even though I would have preferred a different title for it. Acosmism was my favorite title, but then it was suggested that might not attract a lot of audience, so make the title more interesting. So I thought, well, this is a good enough title. So basically, I'll start the journey of physics in a historical context and see where we have ended and where we started. Again, pre-Newton, there was a lot of physics done, but we had to start somewhere if I don't want to spend all time discussing ancient and medieval
Dr.
physics. So
Faizal,
let's start.
can you first like unshare your screen so that the audience can see you first a little bit? Can you interact with the audience a little bit first? Then you can share your presentation.
So audience, so I unshare my screen. Hi audience, this is me online, and now I will share the screen, the more interesting part. Yeah, they can see me also during the Q&A session. Okay, now
great.
Screen. Yeah. Okay, great. Let's go back to this. So I think we have to start somewhere. So I think Newton is a good place to start. So let's start from Newtonian physics. So and the important thing is that I will follow the advice of the editor of Stephen Hawking. I won't use any equations in here. And even though I'll be discussing things which are really complex, I have tried my best to really simplify it. So it will be sometimes oversimplified, hopefully understandable to everyone. And if something is not understandable, please let me know. I will try to explain it better, and we can also discuss it further in the Q&A session. So in Newtonian physics, what is physics? Basically, you have space and time as two independent observer-independent concepts. So what does that really mean? So you have a fixed length, say between 2 points. This length remains the same for anybody, any observer. It does not depend on who is measuring this length. This length between 2 points remains the same. The same thing at time interval between two events. It doesn't matter who is observing it. It does not. It's not in Newtonian physics. It does not make sense to say, between now and me going out of or this lecture lasts for 1 hour, but you can't really say 1 hour for who. 1 hour for you is 1 hour for me. That is how Newtonian physics works. And then universe is made up of material particles, which basically move due to the action of forces, gravitational force being one of such force. And that is all that is to reality. That is it. In Newtonian mechanics, that is it. So, and space in itself is three-dimensional. What does it mean to say space is three-dimensional? Take any point in space, you can draw three perpendicular lines, three lines which are at 90 degrees to each other. So you have three directions to move about. So with this, with this observation, what do we come to? Philosophically, we come to something very interesting. Now, if you know precisely, in principle, it might not be, I don't think it's in practice possible, but you say in principle, you know the position and you know how the exact location and exactly how fast any of all these particles are moving at any point in time, then you can predict exactly where these particles will be at any later point in time and where these particles were at any previous point in time. And in Newtonian physics, since space and time and matter moving in space and time is all that is to reality, you can basically know everything about the universe in principle. And this view is called Laplacian determinism. So everything is fixed. There's no free will, there's no nothing. Everything is fixed. Everything is just motion of particles moving in space and time. And this view, and the philosophical view which develops out of this idea that all that is there to the universe is space and time as two independent concepts, and material particles moving in space and time is called materialism. Basically, all that is there to the universe is material particles moving in space and time. Well, these are some nice references. The first one is a philosophical reference on Newton's view on space-time. And the second one is the third one is a really nice mathematical book introducing Newtonian mechanics or classical mechanics in a more nice mathematical formalism. Basically, it's just Newtonian mechanics dressed up in mathematics. And the last one is a philosophical reference on origins of materialism. Now, this view starts slightly changing when you come to spatial relativity. Why? But not drastically changing, but slightly. Because in spatial relativity, lengths between 2 points and time interval between two events is not something that is universal and observer independent. So time length for me would not be the length for you if we are moving at really high velocities. And by high, I mean velocities comparable to the velocities is a physics technical term for speeds, very high speeds. I will make it really simple. Very high speeds comparable to the speed of light. But however, you can do something else. You can construct a new physical quantity called a space-time interval. You basically take lengths, take time, mix them up mathematically, and you construct this new physical quantity called a space-time interval. And this space-time interval is again same for all observers. So this really means that what we were observing as two physical quantities, space and time, are not really two quantities. They're just parts of a single quantity, single physical quantities, which we should call as space-time. The only thing why we observed them as two independent quantities was because we're moving at very small velocities or speeds relative to each other. And the mixing of space and time becomes really small at such scales. So you can effectively consider them as two separate quantities, even though in reality, they're just one single physical quantity. This also has deep consequences for other things in physics. So everything that depends on space and time, everything that depends on space, any physical quantity that depends on space has a temporal, has a time part of it. So so there is an equivalence between energy and something called momentum, which is basically something called velocity multiplied by mass. But basically, every physical quantity that has a spatial part has a temporal part to it. And in fact, this is the main observation which mathematically produces the relation between energy and mass that has been really popularized. So I hope I'm going simple enough. Again, some nice philosophical references on spatial theory of relativity, something that would benefit general readers, and how space and time, and some really nice physical reference on top about spatial theory of relativity. I just thought I'll give references to everything I say, because I'm going to say controversial things at that, and I need references for that. So you now look at this. You can have something which is flat, like a flat piece of paper, but you can take this piece of paper and make a ball out of it. You can curve it. In spatial relativity, even though space-time is 4-dimensional, you have 3 components of space, 1 component of time. It's flat. General relativity says no. Actually, space-time curves in presence of matter. And gravity that we observe in space and time is nothing but the curvature of space and time. Sorry, the gravity that you observe is nothing but the curvature of space and time. So this makes gravity really special. Whereas other forces move in space and time, gravity is the very geometry of space and time. So again, space and time is not a fixed background in general relativity, it's dynamic. It has a geometry, and this geometry is fixed by the matter that is present in it. It is determined by the matter present in this geometry. So that's a very interesting idea. I have to specify that there are general theory of relativity is not the only theory of gravity at present. There are tons of theories of gravity called modified theories of gravity. Again, in question answer session, if you want to ask me, we can discuss this. This is a really interesting topic and a very interesting topic for research also. There are tons of different theories of gravity, but what all these different theories of gravity have in common is that gravity is the geometry of space and time. I'm not here even saying curvature of space and time for very good reasons. Question answer session, if somebody asks me, I'll tell you why. But now the important point here is that neither general relativity nor any modification of general relativity, any modified theory of gravity changes the concept of materialism. Because now instead of material particles moving in space and time, we have material particles moving in space-time. That's it. Some really nice references again on general theory of relativity first, and then some on modified gravity. I just stuck in my essay here, my GRF essay, which got already mentioned, because this will tell you why I did not use the word why I use the word curvature of. Why I use the word geometry of space and time rather than curvature of space and time for modified theories of gravity. Yeah. Now coming to, but now that's so far so good with general relativity. Now we come to something more interesting, quantum mechanics. Now see, in general relativity, in special relativity, all it stated was that you can't measure like the space the lengths or time don't have observer independent meaning, but space-time does. That's it. General relativity made it dynamic, but still it had observer independent meaning. A space-time interval for one observer was the space-time interval for any observer. Quantum mechanics changes that. Quantum mechanics states, at least in the Copenhagen interpretation, that the very act of observation changes the physical state of a system. And this is very important. The act of observation cannot be represented by a physical interaction. It is really the idea of taking information out of the system, which will be very clear in the next slide. So in quantum mechanics, but the important thing is in quantum mechanics, material particles still remain material particles. It's just not possible to predict their exact location and how fast they are moving exactly. But you remember that I told you Laplacian determinism was based on the idea that if you exactly know the position of every particle in the universe and how fast it's moving, you can basically know where it will be at any later part or at any later part in time, or where it will be at any point of time and where it was at any point of time in past. So, but you can't exactly know the exact position and momentum or position and how fast a particle is moving in quantum mechanics. And it's not a technological limitation. This is how nature is built. In nature, it's not even possible. It's not even sensible to ask how fast a particle is moving after you've exactly fixed its position. And the same thing holds for energy and time, by the way. You can't know what is the exact energy of a particle and at what point this energy was measured. So this really destroys Laplacian determinism. Laplacian determinism has no place in quantum mechanics. I will not dwell deeper into measurement problem of quantum mechanics. Why? Because there are other approaches to quantum mechanics. For example, there's an approach called objective collapse. It's called objective collapse theories, where the wave function actually collapses. Of course, it modifies quantum mechanics in a way. Now, these modifications are small, and it again, they also coincide with all the experimental data we have. It predicts small deviations from quantum mechanics, but these deviations have not been experimentally verified. But the important thing is that there are other approaches to quantum mechanics. Objective collapse models being one of them, environmental decoherence being other, and then there are a set of other really interesting approaches to measurement problems. This is again something interesting if people want to do research. Lift a quantum phenomena, see the effect of objective collapse on on that phenomena. There's one model of quantum mechanics, before I go ahead, that I have to strongly criticize, and it is the many world interpretation of quantum mechanics. Now, many world interpretation should not be confused with multiverse. Again, there are many ideas of multiverse. Please ask me a question about this, because I don't have time to explain this in the slides. I would be happy to discuss how there are different models of multiverse, how some of them can even be experimentally falsified or tested. But these are decent physical theories. What is really strange and what is really, I would say, bad physics and bad philosophy, doesn't make any sense, is the many world interpretation of quantum mechanics. And if someone asks me, I think I have a thought experiment to show that nobody really believes in the many world interpretation of quantum mechanics, even the people who are writing papers on it. Again, something I'll leave for the question session. Some nice questions people can ask me. I'm giving you questions from here only that I would love to answer. So this is some interesting work. Again, some references on the different philosophical consequences of quantum mechanics. This nature and then Copenhagen interpretation of quantum mechanics, and then the 2022 Nature paper is on objective collapse models, where the system actually collapses independent of the observer, but it is a small modification to quantum mechanics, and how this could be tested. And then you have the last paper again about foundations of quantum mechanics, the various approaches to foundations of quantum mechanics. Now, why is quantum mechanics really special? Why? Oh no, what did I do? I did something stupid. Okay, go to downloads. Yep. Okay. Yeah, that shows how good I am with technology. I started as an engineer and I changed to physics, and that you can already understand why. So let's go back to this. So quantum mechanics. We did quantum mechanics. Double slit experiment. That is where we are. Double slit. So I'll tell you how weird quantum mechanics is, and I'll go beyond the usual double slit experiment. There's a reason why I said double slit in space and time. So anybody who knows basic quantum mechanics knows about double slit experiment. You have two slits, basically two holes in a wall. And if you throw a jet of particles towards these holes, they will form a certain pattern. If you throw a wave, like a water wave, towards these two holes, the waves will form a different pattern if you measure them after they have passed through these two slits. That's well known in classical physics. What happens if you take a quantum particle? Well, if you take a quantum particle, if you do not try to measure which slit the quantum particle goes through, then it will form a wave-like pattern. And if you try to exactly obtain the information about where this particle has gone through which of the two slits, then it will form a particle. Then it will form a particle-like pattern. So if you know exactly which slit the particle has gone through, which way information, it's called which way information, which way did the particle go, then it will form a particle like pattern. The important thing here is that this will hold true even if you throw one particle at a time. And the real question is, how did the future particle know that the past particle, you had made a measurement on the past particle or not? A strange effect. The effect starts becoming even more strange if you use a quantum eraser. Now what happened? Now this is the important thing. You throw a particle, you know you do something from which you can actually know the information, or information relating to which slit the particle has gone through. Now it has already passed through this slit, but you do something else to it and you erase this information. You erase the information from about which slit the particle has gone through. And it again goes back to forming a wave pattern. So but it could only have interfered at the point at this double slit, and you have erased the information after it went in the double slit as a particle. How did it again become a wave and interfere? Did the particle know that you were actually going to do this experiment in future? It even keeps becoming weirder. There is a experiment. It's called a delayed choice quantum eraser experiment. And what happens with this delayed choice quantum eraser experiment is that you make a measurement in future. You have two particles, two entangled photons. On one of the photons you make a measurement in future, and it affects the result in past. It's like the past particle changes its behavior because something is going to be done to its partner in future. That is really strange. Something changes in past because you're going to do something in future. And this thing has been even observed in 2000. And this was, by the way, published again in Nature Physics. There's a 2023 Nature Physics called the temporal double slit, where they did a double slit experiment in time, not in space. You can have two slits where in space you have some space where particles are allowed, and then you have a space where particles are not allowed, and then you have a space where particles are allowed. You can do the same thing in time, and you again form interference patterns. The important thing is, how on earth did the particle know that you're going to stop future particles, and why did it change its behavior now? Because you're going to you're going to create a double slit in time. These things are mind-boggling. This really shows that quantum mechanics, there's something really deep about quantum mechanics. It's not just balls hitting balls. There's something really more deeper going on here. And in fact, to give sense to these ideas of delayed choice quantum eraser experiments, concepts like retrocausality or superdeterminism have been proposed. So what is retrocausality? Well, people have argued it's not causality, it's correlation, but in any case, the idea is that future affects past. Causality goes like cause gives rise to effect. Well, no, maybe effect gives rise to cause. It's not, and that's why it's called retrocausality. There's an alternative view. Again, I don't subscribe to this view, but this alternative view says that human free will is a part of nature. So nature not only fixes the behavior of particles, it also fixes your behavior. And so somehow it knows that you're going to do this experiment, and therefore the particles change their behavior today. It is interesting. I have a different view to this, which will be supported by acosmism, which I think is more natural than superdeterminism. But you can see that why these views have come up. One important thing here is that I don't think quantum mechanics. Did I miss that point? Yes, I think I missed writing a point, or I've written it somewhere. But the important thing here is, let's say in quantum mechanics, material particles still remain material particles. We don't know about their behavior. And so I don't think quantum mechanics, even though it has some deep things to say, you could still somehow argue for materialism here, at least in some form, even though there's something more, it's hinting to something more deeper. Again, some really nice papers on first one is on double slit, then on quantum eraser, and then the Nature Physics one is on this delayed choice quantum eraser, and the last paper again in Nature Physics is this recent paper where people have actually been able to demonstrate able to construct temporal double slit in time, where future particles somehow knows what is going to happen to the past particles and adjusts its behavior accordingly. Interesting. That's why quantum mechanics is way more interesting than relativity. Now, it's possible to combine quantum mechanics and special theory of relativity into a consistent theory. Now, quantum mechanics is generally called a first quantized theory. Now, this is done through a process called second quantization. In second quantization, what is basically done is this, that you take an abstract mathematical object called a quantum field. Again, I can expand on it in question answer session. And you basically construct your quantum theory in terms of this abstract mathematical object called quantum field. Particles that we observe, material particles that we observe in nature, exist as approximations, as certain mathematical approximations produced by this quantum field. But this quantum field is more real than these material particles, because this approximation sometimes breaks. I mean, strictly speaking, material particles exist in flat space-time or in some very simple space-times where quantum field can have a certain kind of mathematical decomposition into material particles. So material particles are not really the building blocks of nature, quantum fields are. And that is why quantum fields in quantum field theory, you can explain the creation of and annihilation of particles. Material particles can get created and annihilated. So basically, quantum field theory does to elementary particles what particle physics does to atoms. You see, when you had atoms as indivisible units of building blocks of the universe, at least in chemistry, that's how people thought about it in old times, till people discovered, no, these atoms are actually made up of electrons, protons, and neutrons. And this means that we can split atoms and produce different kind of atoms. In the same way, it was thought that maybe elementary particles, material particles, are the building block of nature, until we discovered, no, that's not actually true. Quantum fields are the building blocks of nature, and the material particles that we have are mathematical approximations produced by these quantum fields. And they can annihilate, they can create other particles, and they might not even be it might not even be possible to have a definition of quantum fields in terms of particles in certain kind of space-times. So basically, also now this and what kind of space-times it's not possible to have a definition of quantum fields in terms of material particles. Well, you can also do quantum field theory on a fixed space-time. So space-time is described by general relativity. It's not quantized, it's left as a classical space-time, but you analyze quantum field theory on it. The quantum fields on this classical space-time are quantized, obey quantum mechanics. The space-time just remains there as something which is not where you do not analyze the quantum effects on space and time. And this theory, where you do not analyze the quantum effects on space-time, but analyze quantum fields on this curved space-time described by general relativity, is called quantum field theory in curved space-time. It's a well-studied branch of physics. So first two books are really nice books on quantum field theory in flat space-time, which is how most people study quantum field theory. And if you are interested in quantum field theory in curved space-time, I thought I'll just put in two references for that too. Now, there are consequences of quantum field theory. I think the most evident consequence is that it ends materialism. Why? Well, you can already see from the previous slide, but let's go more into this. According to special relativity, there is an equivalence between mass and energy. In quantum mechanics, you can't really measure precisely the energy and time, which means that you cannot exactly say that there is no energy precisely at this time, because that's a precise statement, which implies that you can create a very small amount of energy, even though you start with no energy, for a very small amount of time. And this small amount of energy, because of mass energy equivalence, can convert itself into particles. And such particles are actually called virtual particles. Now you would say, well, they remain virtual. They exist only for a very small amount of time, except for the fact that there is an effect called dynamic Casimir effect, where these virtual particles become real. Not only that, Casimir effect has been experimentally observed. It doesn't just stop there. Like, look at this. The bare minimum requirement for something to be objectively real is that there should be intersubjective agreement on it. You and me should agree on something. Otherwise, this something is a gauge choices and is not fundamentally physical. It's a choice that I make. And this is really what we observe with particles. If you have two observers, one of them is accelerating with respect to another, and one of the observers, which is stationary, takes a box and observes that there are no particles in this box, no material particles at all. And the other observer, who is accelerating with respect to this observer, he tries to make a measurement. He will actually observe that this box is full of material particles. So one observer observes the same box, observes that there are no material particles in it. Another observer observes the same box and finds material particles in it. Both these observations are correct, and this effect is called Unruh effect, and it has been experimentally demonstrated. And I think the philosophical consequences of Unruh effect are amazing. The Unruh effect really demonstrates that material particles are not objectively real; they are real to our energy scale they are effectively good description of physical reality, but they are not fundamentally real. Quantum fields are fundamentally real. So that's a really interesting effect. So I would say that quantum field theory, and if more specifically effects like Casimir effect and Unruh effect, experimentally disprove materialism as a philosophy. We are still left with physicalism. There is still a physical field in physical space-time. So we have gone from materialism to physicalism, where we have gone from material particles to quantum fields. Again, some really nice references. The first ones are on Casimir effect, and then you have the references on detection of Casimir effect. Then you have the reference on Unruh effect, and the last one is on the detection of Unruh effect, that it has been experimentally detected, and it has been experimentally detected quite late in 2021. So quite recent work here. But we go further, and now I will tell you that quantum fields cannot also be as fundamental building blocks of nature. Why? Because you can have two theories with very different field content, very different content of these abstract mathematical objects called quantum fields, and yet they could describe the same physics. And these theories are called dual to one another. In fact, in physics, there's a very popular duality called ADS-CFT duality, where you take two completely different theories. One theory is classical curved space-time, And another theory is quantum field theory on a flat space-time. And you actually show that these two theories have the same physical content, so much so that you can do calculations on one and map them onto another. The philosophical consequence of this is, of course, that there's something deeper than just field content. And fields are, again, in more abstract way of speaking, they're not really real in the sense that they still depend. You can have two different theories with two different field contents yet representing the same physics. Again, there's a principle called holographic principle on which ADS-CFT is based, which states that the physics going in the volume of a surface is the same as the physics going on the surface of the surface. But you can already see that the fields in the volume would be different from fields in the surface, yet they can be mapped onto one another. So there is something deeper than field theory, than quantum field theory. But I think what really kills this argument of quantum field theory being the most fundamental aspect of reality is third quantization. See, again, I have no time to get into this, but this is something I have worked extensively on. And please do ask me a question about third quantization. I would love to talk about third quantization. It's something really interesting. But I will try to make it as simple as possible here. Basically, the Unruh effect that I talked about, which occurs in second quantized theories, occurs because of a mathematical technique called Bugolivo transforms. That's a mathematical technique, a certain mathematical technique. Now, it's possible to construct a theory which is called third quantization. Again, I will not get into this in the lecture, but in question answer session, I would love to discuss third quantization. And you can construct an Unruh-like effect in third quantization. But in third quantization, fields play the role of particles, mathematical role of particles. And this theory is not actually defined on space and time. It is defined on this abstract configurational space of fields. And so you can actually demonstrate that field content of one theory, like field content observed by one observer is different from the field content of another observer. Just like particle content of one observer is different from particle content of another observer. In third quantization, the effect is really, the calculations are almost analogous to Unruh effect. And this has been done. And I have references. So you have these references, first references on duality, and then this Maldacena wrote this revolutionary paper on ADS-CFT duality. Then this 2002 paper is on holographic principle, and the remaining papers are on different forms of third quantization. And there's a lot to say here. And Unruh-like calculations in these third quantized theories. I just thought I will stick in this last paper because apart from the fact that it was written by me, it's actually the last 2013 paper. It's actually written on a very interesting topic. It is written on a topic called fourth quantization, and there is just one paper on that, and that's my paper. So there's a joke to this fourth quantization. Again, in the question answer session, I'll be happy to discuss that. But let's now come to quantum gravity. Now we come to the full quantum gravity. So previously we were discussing quantum field theories, at most in curved space-time, but we did not analyze quantum effects on space and time. What happens if you try to analyze quantum effects on space and time? Well, how would you combine general relativity with quantum mechanics? There has been no successful theory of quantum gravity, even though string theorists claim that they have the successful theory of quantum gravity. And I have worked on string theory, so and loop quantum gravity, so I'm not being prejudiced either. But yes, I think it's safe to say that we don't have a successful theory of quantum gravity, but there are various approaches to it. One of them is called loop quantum gravity. Another one of them is called string theory, and there are many different approaches. Wheeler-DeWitt approach, causal sets, Euclidean quantum gravity. All of these are different approaches to quantum gravity. The question is, these approaches are fundamentally different. Have we learned anything? And I would say yes, because these approaches have some universal predictions, some universal features which are common to all of them. And these features are based on certain arguments that you have from physics that you know. And based on the physics of what we know some features that any theory, any of these approaches, and maybe a completely new approach. We develop a completely new approach to quantum gravity, but this theory of quantum gravity should have some features, some features that really there are very good arguments to believe that these features should naturally be part of any theory of quantum gravity. So, for example, we know from black hole physics that no length smaller than Planck length can exist, and no time interval smaller than Planck time can exist. Why? Because if you try to measure space and time at smaller and smaller length scales or time scales, you need to increase the energy. By the time you reach Planck scale, either as Planck length or as Planck time, you basically put in so much energy in that small region of space or time that you actually form a mini black hole. And this mini black hole prevents you from observing that region of space and time. And this suggests that black hole, there's something intrinsic to black hole physics which prevents you from making a trans-Planckian measurement smaller than Planck scale. And since quantum gravity, any theory of quantum gravity has to be consistent with classical theory of black holes, we really expect that Planck length should occur as a minimum, or Planck length and Planck scale over time, basically Planck scale should occur as a minimum scale in quantum gravity. And all theories of quantum gravity do have a minimum scale in one form or another. And an implication that follows from this is that geometry, as we see, is an emergent phenomenon. Space-time emerges. Space-time emerges from something which is not space-time. Basically, just like you can see a chair. A chair has a geometry, a table has a geometry, but you can measure the geometry of table going at smaller and smaller and smaller scales. But the very moment you reach atomic scale, it does not make sense to talk of the geometry of a chair at that scale. In the same way, the background space-time also has a geometrical structure which emerges from non-geometry, and there are very, very good arguments from generic arguments, or in any theory of quantum gravity, this observation holds that space-time emerges from something which is neither in space nor in time. And this holds not only for space-time of our universe, but also the multiverse. So any space-time, spatio-temporal structure has to emerge from something which is not space and time. So some nice references on quantum gravity. So we have this we have some nice references on string theory, on loop quantum gravity, and some nice references on this minimal length. And this is something nice for students who want to do research. These quantum gravity. So we know that minimum length, like space-time, breaks down at Planck scale. What if it breaks down at a scale larger than Planck scale, but smaller than electroweak scale? This can have real-life implications, and they have been studied. For example, in this Nature Physics paper, they proposed an optico-mechanical experiment to detect such things. In this PRL of 2008, this was again proposed. The consequences of minimum time were discussed by me in this 2016 paper. Ted Jacobson has this really nice PRL where he suggests that space-time emerges, the geometry of space-time emerges from something which is essentially thermodynamic in nature. So the question is, what does space-time emerge from if it's not space, not time? Now this gets really interesting. Now this gets at really interesting heart of quantum gravity, where we stand right now. We really have arrived at a theory of neoplatonism. We have really rediscovered neoplatonism in physics. So we went from materialism to physicalism, but I would say now we have gone from when we went from general relativity or quantum mechanics to quantum field theory. But I would say when we go to quantum gravity, there is no way out of neoplatonism. Why? Because space-time structure emerges from information, which is studied using information theory. So what is information theory? It's an axiomatic mathematical system. You have set of rules, a mathematical system with set of axioms, set of rules, that basically makes concrete the abstract idea of knowledge. And this view was actually coined long time ago by Wheeler. The view basically states it is from bit. Substance, it signifies substance, space-time, matter, material fields, quantum fields, everything, substance, concrete, physical, comes from information, idea, knowledge, abstract concept of knowledge, and bit is not from it. So bit denotes this abstract concept of knowledge, concretified using information theory, and it denotes just the substance of the universe. And I made a typo in my science slides. So the laws so this is where we stand. The laws of physics, which are information theoretical processes, are more fundamental than physics itself. The universe or the multiverse exists because of laws of physics. Laws of physics do not exist because of them. So this is quite interesting, really, really interesting. This that the way the observation we have come to, and philosophically, this ends physicalism. We are now in the realm of Neoplatonism. And some nice references on this. I have to stress these different references because this is one point which is the most controversial, which is the most interesting, and which is where basically quantum gravity stands right now, whether you take loop quantum gravity or string theory or any other approach to quantum gravity. I would say, you would end up in information theory. So there is this initial paper, and then there is this Wilczek's Nature paper, which again talks of it from a bit. And then my Nature Review Physics paper that I just recently published, it also tries to talk about the analog, like the analogy between condensed matter and quantum gravity, and again goes on with this view bit from it. There's a Nature paper again on this idea of how information is more fundamental than substance, recently published from string theory group. There's a in this 2019 paper published from loop quantum gravity group, and basically everybody. And then there are a few more papers. Basically everybody's. I think there is almost a de facto consensus that it is from bit is not from it. It's the space-time, and you can already see that generally theory of relativities and effective field theory, it has to come from something more fundamental. Since it describes space-time, that theory which is more fundamental cannot be a theory in space and time, but a theory which produces space and time of the universe or the multiverse. So good, so far so good, but we are still trapped. Now, what have we come to? We have come to an axiomatic structure of a mathematical axiomatic structure being the most fundamental aspect of reality. But it can't be the most fundamental aspect of reality, and here is why. Godel's theorems kill us. Godel's theorem get to us. So Godel, so there is a problem, and this first statement I actually thought of it really nicely. So I'll just read it out. Defining reality as an axiomatic system is also incomplete and cannot be demonstrated to be consistent. And both these words have been placed there because of Godel's first and second theorem. So Godel's first theorem basically states that any axiomatic set, any set of rules is incomplete. So there is, you can construct any mathematical system by stating axioms, stating certain number of rules. This holds, this holds, this holds, this holds. One thing that these rules cannot prove is the existence of something which holds because these rules are true. This is how at least Roger Penrose puts it. But its existence, it can also be proven, it can also be demonstrated that this holds because these rules are true, and it cannot be demonstrated to be true. This is something killing. This is something which has Godel's theorem have shook the foundations of logic and mathematics. So by their very construction, it has been, Godel was able to demonstrate that there are certain statements which are true, but they can never be proven in an algorithmic way that these statements are true. And Godel's second theorem is the killer. It says the consistency of this logical system is one of those. Consistency of this axiomatic structure is one of those things which lies outside this system. So you start with any axiomatic structure, you can't prove that it's complete. There will be something which lies outside this system, and you can't even prove consistency of this system. This produces a fundamental problem. How do humans do mathematics? Because human mathematicians can see these Godelian statements to be true, but it can't be seen if an algorithm is running in our brain, because there is no way to come to these statements through this algorithm. And this has led Penrose and Lucas before Penrose. There's an argument by Lucas Penrose which states that the human consciousness works in a non-algorithmic way. There is something fundamentally non-algorithmic about human consciousness, and this in turn, this non-algorithmic nature of human consciousness, due to this non-algorithmic nature of human consciousness, basically human consciousness doesn't just work as a computational machine. There is something else. You just know without proving. You know it. It's basically concretifying the idea of intuition, if you like. You know it's in some way without proving the validity of Godelian statements, and this is how human mathematicians can prove Godelian statements. And to start with, even the consistency of the original axiomatic set that you started with. This has been criticized though. People have said, well, how do you even know human mind is consistent? Well, maybe human mind is not consistent. It is inconsistent, but its inconsistency is so small that you can neglect it. So there is this argument against Penrose-Lucas argument that human mind is maybe fundamentally inconsistent. And there is a debate between these two sides. But but there are only two possibilities. Either human consciousness is non-algorithmic or it's inconsistent. There is no third possibility. And this is because of the Godelian limitations. Whichever argument you take on human consciousness will not affect why I am trying to say this, because I'm trying to use Godel's theorem for something completely different. And so I'm trying to use Godel's theorem to arrive at a definition of consciousness, which is very difficult to define. If you follow Witten's approach, it can't be defined. But I would prefer Penrose and Lucas's argument to define. It is something that overcomes Godelian limitations and produces a consistent axiomatic structure. So that is, for me, the definition of consciousness. Now look at this, and there are some really nice references here. So some references by Godel, then some references by Lucas, Penrose, and again I have written a paper on consciousness, and some of them are from neurobiology, some of them are from philosophy, psychology. So you can already see that it's and physics. So it's a very interdisciplinary field, and big people are working on this. Now we come to this, the central part or the central conclusion that I want to come to. Humans do mathematics, but reality, we have already demonstrated, is mathematics, is an axiomatic structure. So again, we arrive at the same dilemma. Either reality is inconsistent, or there is something in reality which is non-algorithmic, which can overcome Godel's problems posed by the Godel's theorem. Now, reality by definition cannot be inconsistent because it's real. We will just land into weird form of absurdism if we assume reality is inconsistent. Then we are only left with the possibility that reality is the most fundamental form of reality is pure consciousness. But again, I want to clarify, by pure consciousness, I do not mean human consciousness, which is a low energy effective phenomena in human brain. Rather, I'm using the word consciousness to define. Basically, I'm using the definition of consciousness we developed previously using human mind, but it's not human mind. It's a kind of self-awareness that is needed to overcome the problems posed by the Godel's theorem. So the fundamental aspect of reality can't just be an axiomatic structure and an algorithm which actualizes that axiomatic structure, producing the universe and multiverse. There has to be a non-algorithmic conscious part to it. Like the most fundamental aspect, not part, I would say rather this structure, the axiomatic structure, because how do you even start with an axiomatic structure? The very axiomatic structure and an algorithm producing a consistent universe or a multiverse from this axiomatic structure is produced from something which is non-algorithmic, a non-algorithmic consciousness which overcomes the Godelian limitations. Otherwise, you will end up with a model of reality which is fundamentally inconsistent, and you would end up with in real form of a weird form of absurdism. But this idea that the most fundamental aspect of reality is pure consciousness, and again, I will reiterate, by pure consciousness, I mean a sort of self-awareness which is needed to overcome limitations of Godel's statements. And the criticism of Godel's statements does not apply here because we can't assume that reality is fundamentally inconsistent. So the most fundamental aspect of reality is pure consciousness. Everything else emerges from it. And this point of view is basically already known in philosophy. It's called acosmism. So I think this is really important. So pure consciousness leads to information, which is in turn an axiomatic structure leading to physical laws. Physical laws produce the multiverse, and the multiverse produces this universe, and in this universe we exist. but so this is where we stand. Again, some really nice references to acosmism. Now some philosophical references to acosmism, and this brings me to the end of my discussion. I would have really preferred the title, A Journey from Materialism to Acosmism, even though this title was good enough. So should we open the floor for questions and discussions, which I'm really looking forward to? And should I stop sharing my screens? You guys can see me?
Hello. Can you hear me? Yes.
Hi.
Okay, great discussion. Very quite advanced and very fast-paced breeze through lots of physics and mathematics. So most of our audience was young students. So I think most of you may not have even heard about special relativity, or maybe heard a little bit about special relativity or quantum mechanics. So let me just give you a brief summary of what he talked about. So he first started with Newtonian mechanics. So you have all studied Newton's laws. That is our most basic description of reality, Newton's first law, second law, third law. Then he moved on to Einstein's discovery, which was special relativity, which modified Newton's laws. Because there were some experiments like the Michelson-Morley experiment and stellar aberration and other experiments, which forced us to revise Newton's laws. So beyond Newton's laws, the second step was special relativity. Then came general relativity, which was a modification of special relativity. Then came a new so relativity was a modification of our ideas of space and time. Then came a modification of our ideas of matter. So there are three fundamental aspects of reality: matter, space, and time. All three underwent radical change in the 20th century. So quantum mechanics was our new theory of matter, in which probabilities were introduced, and then new interpretations, which you can ask Dr. Faizal about those as well. There are different kinds of interpretations of quantum mechanics. And then he discussed very different philosophical implications of these changes. So back in Newton's time and before quantum mechanics, everybody thought that everything about the universe can be determined 100%. And that was what he referred to as Laplacian determinism. So Laplace was a scientist living in France. He was a French scientist, and he pronounced that if you give a computer or a mind all the information about the universe, like the position and velocities of all the particles, then he can determine everything about the universe. But after quantum mechanics, you know that in quantum mechanics you can't predict everything with 100% certainty. So that view was abolished, and then we determined from determinism we arrived at indeterminism. And then he discussed other implications, like quantum mechanics was upgraded to quantum field theory. And in quantum field theory, matter doesn't no longer plays a central role, because matter can come into existence and out of existence. The most fundamental thing is fields. So from matter, materialism was abolished, and from that we arrived at physicalism. So there is something physical about the universe. Those are quantum fields and not matter. So particles are not fundamental, but fields are fundamental. And from there he talked about quantum gravity. In quantum gravity, when you go to the Planck scale, space and time have to be rethought. So space and time turn out to be approximations, and we all think that space and time are the most fundamental, right? How can there be something more fundamental than space and time? But we have to arrive at something more different than space and time, because space and time completely break down at the smallest scales. And then there is lots to be discussed about the philosophical philosophical approach that he is taking. Many criticisms can be made on that as well. So so first let me ask a few questions. In philosophy of science, many people criticize scientists and science generally. For example, those who are against science or against the method of science, they say that your theories keep on changing. First you had Newton's laws, then you had relativity, then you had quantum mechanics. If your fundamental things keep on changing in every generation, then how can we trust science? So from that, a new approach was proposed by philosophers called structural realism, in which the structure of the laws remains constant, but the entities change. Can you talk a little bit about that?
Well,
Structural
I'll tell you my
realism.
own approach. My own approach is really based a more theoretical physicist approach, and it's really based on effective field theories. So I would say that any statement in physics, except the absolute statements that where you have to discard everything and where you finally end up with the most fundamental aspect of reality. And I would really like to learn from you what criticisms you can make from this, because I haven't found a criticism so far, and I would love to hear that. But coming back to this very approach. So apart from that most fundamental aspect of reality, which is by definition fundamental, any other statement made about physical use, any other statement made about reality, and especially physical reality, is an effective statement, holds at a certain scale and breaks at a certain different scale. Take something simple. Take a rod. You can put some force on it. The rod bends. The rod bends. The more force, the more bending. The more force, the more bending. Then this gives you effectively a law of physics, Hooke's law. But this, as soon as the rod bends, this law holds no longer. If you try to now simulate this, a small force will cause infinite bending after the rod has broken. Why? Because this law that we had, bending of the rod proportional to force, is not the most fundamental aspect of reality. It was an emergent law which emerged from atomic physics. Now, atomic physics is good to describe a lot of physical phenomena. But then there are paradoxes you would get if you just assume atoms are the most fundamental aspect of reality, and then you have to go to something more fundamental, which is particle physics. So I would say that apart from the most fundamental aspect of reality, any statement is an emergent statement. And that is the philosophy of effective field theories. What do effective field theories say? Take Weinberg-Salam's model. Nobody thinks that standard model is really fundamental, but it's good enough description of particle physics, because scales or energy scales to which it describes particle physics is the scales to which we have tested particle physics and any higher energy scales, we just integrate them away. We just throw them away. We just fix them in the arbitrary constants of the theory. So I would take this approach, the approach motivated by effective field theory, and I would say that any scientific statement is only true to a certain level of approximation, and it is only true to a certain level of validity, and it's also true only to a certain level of accuracy to which we have tested this statement. Now, what are the implications of this approach? Take Earth. Well, we say Earth is a sphere, Earth is a spheroid. Maybe we make a more precise more precise measurement and come up with a better geometrical shape, which would be better describing Earth. Slightly modified spheroid, okay, fair enough. Something else. But if somebody comes up and says Earth is a triangle, this is a wrong statement. You see my point? So any statement that you make is valid only to a certain accuracy to which that statement has been tested. Of course, by definition, by their very construction, they have to be modified beyond the level at which they have been tested. And that is the whole philosophy of effective field theories. That is the philosophy on which quantum field theory works. That is the philosophy on which every physical theory works. And that is why we see constants in nature.
Yeah, so I think your approach is the same as the structural realist, because the entities keep changing, but the basic laws behind them, underlying them, they maintain a kind of structure. But the second point that I was trying to make
I would slightly disagree, because I would say that even the laws, that what we call laws, not the fundamental laws. The fundamental laws, the most fundamental being, as I said, a non-algorithmic consciousness producing some information theoretical structure. But say but the word law really applies to an information theoretical structure, not to the non-algorithmic based producing it. But let's come to this information theoretical structure. Yes, that precisely would never change. But I would say that the ways we approximate this ultimate law effectively to various circumstances is different, and we do not know the approximate of this ultimate law, and even if we knew, it would have very limited applicability. I mean, you do not need to know relativity, and even to measure how you would construct a building, and even if you know relativity, you won't use relativity in measuring the forces that are acting on a rod. It would make no sense to use that. And so in this sense, most of the practical aspects of science that we observe, we don't start from first principle. Nobody says, okay, let's start from the theory of quantum gravity and let's see how we should build this building or how a jet should fly. That's not how we do calculations. Yes. We know that a good theory for this purpose is this approximation, and this is all we care about. We integrate the rest. So I am different from structural analysis. No, I would say I'm effective field theory based. And this is really what we do in physics. Everything else is different. What we really do is we do change our laws. We effectively approximate our laws. And those approximations are good enough for our scale. In philosophy, the closest I would say to philosophy is this idea of tanzil. By the way, since I mentioned it, this idea of acosmism has been referred heavily in the philosophy of both, in proper Western philosophy and Eastern philosophy and philosophy of religions. And even in Islamic philosophy, this is called basically Wahdatul Wajud. And in Hinduism, it's called Advait Vedanta. We can get into that. It's just motivating questions. And there is this idea of approximation of tanzil or reduction of this ultimate to various effective approaches that we see. I would say that is my approach.
Yes,
my approach is the reduction of the ultimate or approximation of the ultimate to simpler situation. That is what we do.
Yes, very fascinating. Let me just ask one more question and then we can pass on to the audience, because audience also may have many questions, since it is a very broad topic.
This question where you find a problem with my approach. You just said there is a problem with my approach.
Just a question. I can't really identify major problems with just upon the first hearing. But your it from bit slide, in which you mentioned it from bit. So you basically, you from materialism, you went to physicalism. Right, and from physicalism you went to information theory, that laws are the most fundamental, and you made the statement that I think reality does not determine laws determine the reality.
Physics determines the law. The law determines the universe.
Yes, the universe does not determine the laws determine the universe. But you made that leap by looking at quantum gravity, right? And in quantum gravity, at the Planck scale, space and time have to be modified. But we don't yet have a theory of quantum gravity, right? when we have a theory of quantum gravity, maybe we will have a new kind of substance, a new kind of physical thing that is present at the quantum gravity scale. So we, before having a quantum gravity, maybe a new ontology will emerge, right? When we do have a complete theory of quantum gravity, it will be different from fields, it will be different from our current ontology, but a new ontology might emerge. So I don't think we can throw physicalism out of the picture before we even have a theory of quantum gravity, right? That's what I
That
was
is one
saying.
of the most amazing questions I have heard. That's really nice. I love this question. Yes, and my whole approach was this: that even though, see, if I was a string theorist, you could catch me, but I worked on string theory. If I was working on loop quantum gravity, you would catch me saying, tell me that there are flaws in loop quantum gravity, and I would accept it. But I'm somebody who's a quantum gravity perennialist. I have seen different approaches to quantum gravity, and I was not basing my argument on one single approach. I am basing my argument on universal features of these approach. And if you go back to my slides, I actually stated that there are some universal features of quantum gravity, and there are very good reasons to believe in these universal approaches, these universal features. There are actually nice papers written on this. In this slide, let's go back to my slides for a minute. If I can go back 1 minute, I don't know. Yeah, sorry. Let's go back to this one. This one. Let's go back to this. So this paper. Where is this? Yeah. So yeah, even in this paper, this PRL paper, it's based.
You can share your screen. Have you shared your screen?
Okay.
Please share your screen
I will
first.
just see. Yeah. Wait a second. Let me do this. This is getting really interesting. I got a really lovely question. That's one of the best questions I have got so far. So yeah. So let's get back to this. Yeah. So in this PRL paper, it was actually argued that the minimum length is a universal feature of any theory of quantum gravity. In this 1993 paper, it was argued that any theory of quantum gravity, whatever theory it be, if you can come up with a completely different theory, you have to discard space and time, because space and time will break at Planck scale due to very general considerations from black hole physics. They follow from black hole physics to any number of other considerations. And I'll tell you a very simple thing. General theory of let me stop sharing another screen. So the general theory of relativity is an effective field theory. Nobody denies it. It's an effective field theory because it develops singularities. You develop singularities at the center of the black holes. You develop singularities at the beginning of the universe. Singularities are basically places where physical laws don't work. And I'll tell you a very simple place where you can develop singularity. You have the Hooke's law, force proportional to bending. Break the law, break the rod, and simulate it in a computer. A small force will produce infinite level amount of bending. You will get a singularity. Singularity basically develop when you are approximating a system, using an approximation on a system beyond the validity of that approximation. So the fact that you can develop a singularity at the center of the black hole and the beginning of the universe, the Big Bang singularity and the essential singularity, which you cannot do away with by a coordinate transformation, at the center of the black hole, implies that general theory of relativity has to be an effective field theory. Now, if general theory of relativity or any modified theory of quantum gravity describes space and time, this effective theory cannot be a theory in space and time. The idea that Planck scale breaks up is something that you can even argue from very generic principles, and we can go into this, how generic and how rigorous these arguments are. So let's assume all the theories of quantum gravity are wrong. Loop quantum gravity is wrong, string theory is wrong, Wheeler-DeWitt approach is wrong, Euclidean quantum gravity is wrong. These generic features still will hold. And these generic features are based on things we know, we have experimentally detected. Like black hole physics, and you would say how black hole physics has been detected, analogs. Same physics have the same, solution, same equations have the same solutions. So I would say that it would be impossible to retain space and time. Impossible.
Yes. Okay, great. We can continue this discussion. We can also have like private meetings, and we've already had a meeting in which we discussed a lot of things. So let me open it up to the audience. They might have a lot of questions. Let's give it to Sir Pervez Hoodboy first.
Yes, please.
Hello, Faizal. Good to see you.
Hi, good to see you finally after email exchanges.
First time I'm seeing you, actually.
Yes.
First, a little correction. I don't think the Unruh effect has been seen. The Unruh effect.
It has 2021.
No, it has not. Because you need the amount of acceleration that you need would be just far beyond anything that can be physically obtained. What has been seen is something in atomic physics and it is something that simulates the Unruh effect. It is not the Unruh effect, but that's a quibble. Let that be for
Okay.
now.
We'll come back to this
Yeah,
one.
you can check your references on that.
I'll check my
Yeah, okay. Yeah, because
papers.
you cannot possibly have an observer that accelerates at the
Uh,
rate
I
where you can actually see the black body distribution of radiation as seen by the observer. That's not possible. That simply cannot be done. It can be simulated. Okay. My bigger worry is, all this acosmism, what's it getting you? I know what the standard model did. Okay, the standard model made a set of predictions that were possible, that were tested, and were tested again and again. Right? We knew that the standard model was not complete. We knew that those 18 fundamental particles were not really fundamental, and so we went and created string theory. And okay, string theory has its own history. It's not complete, certainly. It hasn't made any predictions, but at least you have a sort of overarching structure which could someday lead to that. But in terms of this acosmism, what's it going to give me in terms of a prediction? What I want, you see, I'm very old-fashioned. I belong to the old generation of physicists, okay? So I know that second quantization fields, they were important in getting us to many different places. They helped us they helped us get to the standard model, which is actually the only thing that really works. And of course, a lot of a lot of things in condensed matter physics where you can simulate with fields, all that is good, and it is solid physics, because physics is all about making predictions of physical phenomena. Now, if you get into matters of consciousness and quantum gravity as having some connection with consciousness, well, then I'm going to ask you, how many angels can dance at the tip of a pin? You're going to be back into the dark ages if you let go of physics having no connection with reality. So I am a little skeptical of all this, pardon me, but I'm not convinced at all.
Okay.
Yes, Dr.
Yeah. First, a quick thing. Let me just reshare my screen. So, a quick comment. Again, this is, even though this is a very simple resource, but even the Wikipedia article does state that if you see there, and of course these papers have been done. So Unruh effect may have been seen in 2019 in CERN. We can get into the details. Am I sharing
tell me
my
how.
screen?
Tell me how.
Well, we can get into those details, into what has been actually seen. But let's come to the main question. Which is more interesting. And Unruh effect definitely will come to that. It's very
Yeah,
interesting.
that's a minor. Unruh is minor. What is major is what is the prediction that you're going to give, which I can go out and test.
So, okay, let's come to this one. Why has T-duality been invented? Why has string theory been invented? Why has loop quantum gravity been invented? Why do we even care about what happens at the center of the black holes? We can never test it. We can never test it. We can't even in principle test it.
Oh,
So
but wait a minute. Information lost in the black hole is fundamental to quantum mechanics.
No, but
if you lose information over there, then the basics of quantum mechanics is gone. What's this going to give us?
No, just a second. Information is an IR problem. It's not a UV problem. Why do we talk about UV completions of a black hole? Why do we talk about UV completions of quantum gravity at the black hole? This thing can be never tested. The singularity, removing of singularity, I can guarantee you that this will never be tested.
There was a theoretical problem, which is why
No, but this is
people spend so much time trying to prove unitarity.
No, but consistency. Now you're coming to it. It's not experimental tests. We're not talking of technology. We're not talking of experimental tests. There is no experiment. Let me make it very clear. There is no standard model is something you can test in CERN. Yes. Anything beyond standard model, when we are talking of these fundamental, especially quantum gravitational phenomena, where you are challenging the very nature of space and time, I'll tell you a few things that people have spent their life on, and people have done huge work. And we're talking of real big names in physics, and none of these theories can in principle even be tested, but there are these problems. Information theory, yes, the information theory is a problem that you could say, well, in future, maybe an alien civilization goes near a black hole and can still test it. But the essential singularity at the center of the black hole, how on earth will you test it? Nobody can test it. No, but it is a prediction of general theory of relativity, which implies general theory of relativity is not UV complete. Why do we care to have a UV complete theory, which can never be experimented?
But there was a problem over there, wasn't that? That of unitarity.
No, the problem was consistency.
So here you're starting even without a problem, and then you're building on that. I mean, you have to have a definite problem, some definite challenge. Where's the challenge here?
No, but here the challenge is mathematical Godel's theorems. The challenge is I see. For example, till the level of acosmism, let's leave acosmism because that is based on Godel's theorem. Let's go to the problem of space-time being fundamental, where I go from bit to it. There are obvious space-time can obviously not be fundamental. It breaks down. It's represented by general theory of relativity, and the problem here we're dealing is purely a philosophical problem of consistency. There is no experimental. And I will challenge anybody, there is no experimental, not even an alien civilization, not even a type 7 civilization can measure the
Then it's not science.
Then
it's not science. Then you're doing something else.
You can say string theory is not science. You can say quantum. You can go on with the view. Even look, quantum gravity is not science. You can go on with the. Is quantum mechanics science? Is the work on foundation?
Oh yes. Quantum mechanics is it's my bread and butter. And I tell you, we make predictions, and those predictions can be tested.
Foundations. Found people who are measuring on measurement theory. Between Copenhagen interpretation. Again, I do not consider. I think we would possibly agree that many world interpretation. We both might not consider science, but the debate between many world and Copenhagen interpretation, old one. What are the predictions? And the whole idea. What are the predictions? Let's address this problem. What are the predictions at the center of the like? There is an essential singularity at the center of black holes. Do you agree with that? Which can't be removed through coordinate transformation.
Of course, we're not going to get to the center of the black hole. Of course not.
Yeah, but there is a problem,
but
right?
There have been very rich spin-offs from there. The whole idea of holography, the whole idea that all the information resides on the surface of the black hole. That's very rich. That's what gives you Maldacena and all.
What motivates the whole thing? What motivates the whole thing? Because really, if you're let's break it down. Let's break it down so both of us can see why we disagree. And it's fine to disagree, but this is the whole point. I don't think it's a consistent stand to have. I think it's an inconsistent stand to have that the only requirement for a scientific theory is experimental predictability. It's a stand because this stand, again, people who have argued against string theory have used this stand. I don't think it's a consistent stand because the best work in science that is done is not done in this way. The most deepest problems, and you would agree that information theory is a deep problem. The information theory is again something we can't actually physically test. Hawking radiation is too weak. But
information theory is very valuable, and it comes in a very important way. When you look at entangled states, the entropy that is in there, whether the black hole actually destroys or adds to the entropy, whatever. But anyway, I'm not going to take more time because there are other people who have questions.
No, but this is really interesting. Let me just develop on this. Let me just develop on it, and then we'll move on. My whole stand is this: that I think it's a very old, maybe this stand that every theory can be, that exists. Anything that is physically valid is that which can be tested. It's a thing that people say, but it has no validity because a lot of work done in science by one of the best scientists, published in Nature, by Nobel laureates, by everybody. I quoted a bunch of papers for this, actually is based on problems of consistency rather than problems of testability. You have problems with general theory of relativity. You develop a singularity, everything breaks down, space-time breakdown at the center of the black holes, at the beginning of the universe. Everybody believes that you have to have a consistent theory of nature, and to do that, but there is no experiment you can do because you can't even reach the singularity. It's covered by event horizon, and that's it. You can't do an experiment from outside the event horizon to know about what goes on inside the event horizon. And I can give you example after example after example. Let's one simple example, and then we can have more discussion with the students. Take the cosmological constant problem. Everybody is working on cosmological constant problem. I have proposed some solutions to cosmological constant problem. Cosmological constant problem states that the cosmological, like you basically develop extreme, really exotic mechanisms to explain why the value of the cosmological constant is the way it is. But let's assume what are you if you accept one of these mechanisms, how many new things are you accepting? One new thing. And if I just accept a fine-tuned value of cosmological, how many new things am I accepting? One new thing. I would really honestly say that one of the big myths about physics is that we just connect the dots and that's how we develop theories. No, the theories are really developed for mathematical beauty. That's how Dirac developed his equation. That's how lots of even Maxwell developed his equation, and then consequences follow. So a lot of these physical theories are not motivated by just trying to explain the experimental data with dots. They are developed because of beauty, because of mathematical beauty. That's how Dirac developed his theory. That's how lots and lots of physical theories have been developed. And some of these theories are developed for pure problems of consistency. And so what guides us in physics really before even the scientific methods is a search for beauty and consistency. And a search for beauty and consistency, you cannot run away from information theoretical aspects to reality. Space-time has to break down, and if information is there, you can't run away from Godel's theorem unless you deny mathematics.
Another example of untestable idea that was advocated by a lot of great scientists, including Weinberg, was the idea of the multiverse, right? To explain fine-tuning as well as the cosmological constant problem. So that is a totally untestable idea, but is like advocated for by many of the leading scientists, both current and past.
Coleman, my multiverse, and since you brought up the multiverse is amazing.
Yes, can we take a question from a student?
Please.
You can, yes. Yes, please.
Dr. Mir, thank you so much for a great presentation. The the concept of acosmism is really interesting and something to ponder upon. So my question might sound a little layman, but I want to know, why do we require the consciousness to be algorithmic, or what does it even mean for the consciousness to be algorithmic or non-algorithmic?
So this is really interesting. This goes back to Roger Penrose's original view on consciousness. Of course, his view was not about universal consciousness that I'm advocating. His view was about human consciousness. There have been criticisms of this also. So Godel is a mathematician. He proved two important theorems in mathematics, which have basically shaken the foundations of mathematics. And the simplest way I can explain these theorems is this: that there are certain axiomatic structures. There are a set of rules. You start from a set of rules and prove the corollaries. In mathematics, that's what you do. You start a set of rules and end up in corollaries. End up proving corollaries. Yeah. So so with this idea that you can use a set of rules to prove corollaries. Now, what Penrose argues, and this is a really nice way of putting Godel's theorem also in the perspective of consciousness, is that there are certain things which are true by the very construction of these rules, but they can never be proved to be true if you believe those rules are true. And this is essentially the essence of Godel's theorem. But human mathematicians can see them to be true. And that means that what works in a human consciousness is not an algorithmic process. It's not a set of rules that you go from one to another. You can't have a proof of that. A computational machine, a computer could not prove this. I'll give you a simple statement. If you have the statement 1, statement 1 says statement 2 is true. And statement 2 says statement 1 can never be demonstrated to be true. Now, a human can immediately see if statement 1 and 2 can be true at the same time, whereas a machine can never do that. And this shows that there is something non-computational going on here in human consciousness. Now, the criticism of Penrose's view has been done by certain philosophers, and they've said, well, it might be that human thought is fundamentally inconsistent. It works by some paraconsistent logic. But that does not change my argument. My argument was applying it to a completely different scenario. But this is how Godel's theorem works out with consciousness.
Thank you.
Oh yeah, by the way, I just remembered something which goes out to our older discussion. There's a really nice paper by Robert Mann where he proposes that Berry phase in accelerating observers can actually be used to detect Unruh effect. Again, something. This is again from the point of view of Unruh effect. If Parvez, if you want, we can actually look into this more. And the idea of Berry phase affecting the Unruh detectors is so amazing that a young student can lift it, and we can actually see the gap corrections on it. And this is something which would be really publishable and interesting.
Yes,
And
next
this can be
question.
actually possibly done.
Let's have the next question.
Sir, thank you for simplifying such complex topics. So, after the Newtonian laws and when it progressed through technology and engineering and productization, we got some amazing inventions like cars and elevators and space rockets. So, after these quantum gravities and stuff, go through those cycles of engineering technology, what gadgets, what useful inventions do we foresee in next few centuries?
Okay, I'll tell you an honest answer to this. You know all the money spent on CERN? What are the technological implications of it? Nothing. There is no technology below nanoscale. I can't conceive of technology below nanoscale. Why are we constructing CERN? Because we are trying to identify the fundamental laws of physics. Man does not live by bread alone. There is more to reality that I can't
There have been
conceive of.
space technological spin-offs from CERN, radioactive medicine and the superconductors.
Yeah, but
That have
radioactivity
been
is not
used
at the
in
scale
other
of
applications as well. So there
well,
can
you
be
might,
spin-offs.
yeah. Yeah, radioactivity is not at the, to understand radioactivity, you don't not need to go beyond standard model. The radioactivity is nicely explained by nuclear physics, and there's a disconnect between nuclear physics and particle physics. Like nobody has been able to derive nuclear. This is something even Parvez can explain better than me.
Also, the
Nobody.
internet was invented at CERN. Yes,
Which one?
the internet
No, but
was.
okay, these are spin-offs. I agree. You
Yes,
can have lots of nice
spin-offs I'm
spin-offs.
talking about.
We can have, but the fundamental idea that like atomic physics has direct technological implications. Particle physics does not have implications. Maybe some spin-offs. And quantum gravity, I can not even think of a weird way in which quantum gravity can have applications. What are the applications of T-duality in string theory? Zero. I can't think of any. ADS-CFT, yes, it's a good computational device, but ADS-CFT is not real quantum, not real quantum gravity. You have a background space. What are the implications of problem of time that people have spent their life on? Nothing. What are the implications of Euclidean quantum gravity project of Hawking? Nothing. So we have to agree that quantum gravity and some of these deep questions in physics don't have technological implications. People pretend that they have. I'm not one of those people. Like people come up and say, oh, I've heard people say that quantum gravity has helped us understand graphene. Well, yes, I've done a paper on quantum gravity and graphene, but I could have very well done that paper without understanding quantum gravity. So let's be honest that we are trying to identify fundamental laws of physics. There are areas of pure mathematics and pure physics which don't have technological implications. And I think we should not be so pragmatically driven that everything is driven by technology. That's not how humans live. The humans live by, there's something more to life than technology, and it's the quest for knowledge for the sake of knowledge.
Can you talk a little bit about quantum computing? Can our search for the fundamental laws of physics, can it add to the quantum computing space? Because that is like
Okay,
one of
that's
the
a
cutting
project
edge.
we could do together. This is something we were discussing. So again, the idea is that quantum gravity can have a back reaction on low energy back reaction on quantum computing, on quantum mechanics. Something we discussed last time. We were discussing a research project last year, if you remember. Now people have thoroughly studied the low energy effects of quantum gravity on quantum mechanics. What people have not studied and not thoroughly studied, I think we did a paper recently on that, but not many papers on that, is the effect, or is the low energy effect of these quantum gravitational corrections on quantum computing. Also people have, and this is something again where we discuss, models like materials like graphene can simulate quantum gravitational effects. They can also be used as quantum computers. So it might even be, this might be actually, okay, this might be a place I'm self-contradicting myself, because you might learn something from low energy implications of quantum gravity in materials like graphene, and that can have analog application, like the analog quantum gravitational models can have applications in real computing. But yes, you can possibly do that. We can, if we want to do that, we can actually do some really cool work here. For example, we can look at these, we were discussing these higher order corrections to the Dirac structure of graphene. We can actually look at how that affects quantum computing, and that's something interesting.
Yes, so maybe these latest advancements in physics, they can lead to better quantum computers. That's one thing that I can think of. Yes.
I came here to listen a lecture about physics, but it was more about metaphysics, I believe. I personally have interest in philosophy, and I think you have used so many philosophical concepts in such a brief period of time. Without even explaining any of them. I mean, with your pace, my processor cannot actually process information with the pace you were going on. Anyway, I would just ask a few questions. You talked about mathematical beauty, you talked about consistency, and you talked about consciousness, all of which are not the scientific terms as yet. How do you define them? And do you think that they are fundamental properties that we should study in order to do science? And secondly, what Karl Popper says about the falsifiability of the scientific claim. And the third thing that I would say is about Godel's theorem, which actually is about, Wittgenstein actually said that it is all language game. So he thought that all philosophical problems are actually linguistic problems. So, and that is exactly what I found. It is a cyclical argument. Godel actually says that you cannot prove it, or it's incomplete within that system, not from another system. And
Yes. But then
that makes it a cyclical argument, actually, which is a linguistic argument rather than the philosophical one. So I need your input on all these three things.
So let's start by one by
yeah,
one.
I hope
let's see
I have
what
cleared
follow.
myself.
Yeah. But can you help me in one way? Just codify your questions one by one so I can respond one by one.
First
This
was
was
that
super
define
generic.
your terms.
The first one
maybe
was,
you can help me.
do you think these are
First was-
important properties, consciousness, mathematical beauty, consistency?
Yeah. So consciousness. I don't take Witten's approach to consciousness, where he says we can never know what consciousness is, and this will always remain a metaphenomena. I do take Penrose's approach to consciousness, where he says that consciousness is something non-algorithmic, which overcomes the Godelian limitation. That is my approach to consciousness. Consistency is, yes, consistency is more straightforward. You know, consistency of a system is that you have a set of rules. You use a certain use a certain kind of algorithm to arrive at one conclusion, and you use a different algorithm to arrive for the same conclusion. You arrive at a contradictory conclusion. So there's something fundamentally wrong in the initial algorithms you chose. They are contradictory. They are not consistent. That is what consistency is. And consciousness. So we did consciousness, consistency, mathematical beauty. Mathematical beauty is something interesting. I haven't spoken about it, but this is something interesting. So what we observe, and this is, I think, really how progress is made in science. Progress is not made in science by just looking at experimental data and trying to data fix. That is what engineers do. And that is why I left engineering. Progress is made by science by seeing that there are bunch of equations, bunch of data, bunch of structure, and trying to find a meta structure which explains all that structure. So, for example, there was a problem. People knew relativity is correct. People knew, but the first quantized theory of, if you directly first quantized relativity, you got into all kinds of paradoxes. And Dirac tried to invent his theory to make at least to arrive at one equation which is consistent as a first quantized equation from a relativistic point of view. And he arrived at Dirac equation. So he was looking really for beauty, and he discovered Dirac equation as a consequence. So it is not like he was looking for truth. He was looking for beauty. He was looking for mathematical consistency. And what he derived as a consequence, as a byproduct was truth. So and that is, I think, how people might not say it, but that's really how research on fundamental physics works. I get papers for review. Lots of papers, people get papers for review. How do you define? How do you judge whether this paper should be published in PRL, PRD, or a local journal, or it shouldn't be published at all? How do you judge it? Most of these papers do. If you're not a phenomenologist, if you're not an atomic physicist, a nuclear physicist, a strict particle physics phenomenologist, if you're working on something really fundamental, you're working on the fundamental structures, there's not much you can do with experiments. So what really makes string theory an amazing theory, where best minds of the world are working on it, and another theory, not so amazing theory of quantum gravity, it's mathematical structures and beauty and consistency. That's it. So there is the level of structures and the level of consistency. And I'll tell you something really interesting where consistency and structures and mathematical beauty comes in. You had something very simple. You had Newton's laws explaining how planets move. And then you discovered an anomaly. Anomaly was that the Newton's laws don't explain the moving of Mercury nicely. Now you could take two approaches to this. You could take an approach and say, universe is approximately consistent, the universe is fundamentally inconsistent, there is no reason for universe to be mathematical, and maybe universe is not mathematical. Or you could take the approach that we have not discovered a law as yet, but universe is always run by a consistent physical law, and what we have discovered is a small part of that consistent physical law, but the universe is run by a more beautiful, more consistent, more elegant law, and what we have is only an approximation of that law. But before the discovery of that law, the belief in such a law is just a belief. And of course Einstein believed it, and he discovered the Einstein theory of relativity. Standard model, apart from having some problems, is a good model to explain particle physics. It has a bunch of fundamental constants, and even as Parvez said, nobody believes it to be a fundamental theory. Why? Because there are just lots and lots of constants, and it looks ugly with a theory with so many constants. Why is nature arbitrarily choosing the value of these constants? But it's a good theory. It explains all the experimental data. Why do we believe that it's not a fundamental theory? The only reason we believe in it not to be a fundamental theory is because it's not beautiful enough. It's not cute enough. We need a theory where these.
Also, it's incomplete.
Exactly that. That's what I wanted to ask. I mean, what's more important? Are we after truth or after beauty or elegance?
No way. Truth is a dark array. For people like me who do quantum gravity, who do physics at a scale which cannot be fixed by experiments, and even in all honesty, for people who are doing anything beyond phenomenology, truth is a dark place. How do you search for truth? You search for truth through beauty. There's a beautiful saying in Hindu tradition, Satyam Shivam Sundaram. Beauty, truth, and God, they're identified. The ultimate reality is beautiful and beauty is truth. So you go after truth, you attain beauty. I mean, you go after beauty, you attain truth. Going after truth,
but
mathematically is
what if reality is not beautiful? What if it's not elegant? How do... I mean, it's simply a belief.
I don't think we consider the possibility.
I think it's better we move on to the second question. Don't you think?
That would lead us to absurdism, and I think one thing we can all agree on mutually is that we have to reject absurdism.
Yes,
so what's your philosophy of science? Okay, just let me ask you just one question.
Ultimate reality can be explained through acosmism, and everything else is an emergent phenomena which can be explained through effective field theories.
Well, that's your belief. I'm asking about the philosophy of science that you adhere to.
So for me, how science fundamentally works is that you go after beauty because the ultimate laws are beautiful. What you discover, and this is really there. For example, let's put it. People might not say it as explicitly as me, but everyone is doing it. People have spent their lives discussing supersymmetry, and you know what is the experimental evidence of supersymmetry? Nothing at all. String theory is based on supersymmetry. So the best minds in the Stanford list when it came out, maybe the top 10 physicists were string theorists. Witten is string theorist, Maldacena is string theorist. Name any top string physicist, he might be a string theorist. What is string theory based on? Supersymmetry. What is the proof of supersymmetry? There is no experimental proof. Why do people spend their lives discussing supersymmetry and string theory? Because it's beautiful. Beauty is the guiding principle.
Thank you.
And that follows because ultimate reality is self-conscious.
Hello, sir. I wanted to ask, when you talked about that quantum particles collapse when they are measured, they must be measured by someone or an observer. Who is that observer exactly? Could it be a
So,
machine, or
oh
is
my
it
God,
just
so you
consciousness that
are
counts
asking
as
me
them?
one of the most difficult questions in physics. This is the crux of, this is one of the most difficult questions in physics. In fact, Feynman, before answering this question, Richard Feynman actually said something really interesting about it. He said, well, this is an actual quote, that there was a time when people said that, people said that only 3 people or 2 people, exactly remember, understood general relativity. I don't think there was ever such a time. On the other hand, it's safe to say that nobody understands quantum mechanics. So it's pretty it's pretty clear that this is one of the most difficult problems, because see, the person who is observing it, you usually take the measurement device, but then the measurement device is made of quantum particles, and this has led to a problem called Copenhagen interpretation. We don't address this, but this has led to a really big debate. To answer your question in all honesty, I mean, people have turned around on this and said, well, the device is conscious, and some people have even made conscious observers and as a meta phenomena. I think the only way around it is that we have to discard Copenhagen interpretation of quantum mechanics. We have to go to some objective collapse models. I thought about it a lot. I'm not able to reconcile. I mean, I could give you an answer, but that answer should be that something I am satisfied with. I could tell you in Copenhagen and interpretation, you just view yourself as a classical observer and decouple yourself from the system and make the measurement. But then you can come up and say that I am made up of quantum particles too. So I am not convinced. So I can't speak passionately about this because I'm not convinced. I could speak passionately about things I am convinced. I really think, in all honesty, quantum mechanics has to be replaced by some kind of objective collapse models, something like Penrose's model where gravitational field causes collapse, or some kind of stochastic terms. There are lots of these models. I just quoted US Nature Physics paper on this. So there are lots of models. Yes.
Are there any other questions?
And that is
Sir.
really an honest answer.
So could you clearly define acosmism, and what is the future? What's the future that you see in this area? What you have, the area you're focusing on now, and what's ahead? What do you want to focus on in the future?
So acosmism is actually a term used to define the view of Spinoza. I think am I pronouncing his word wrong? You're the expert here
Spinoza.
On Spinoza. Yes. So sorry, that is the Spinoza. Yeah, got this name wrong. Spinoza. So the acosmism is basically this was like, people thought he was a pantheist, but then it was discovered like people, when they really dwell deep in his views, that he's not a pantheist, he's an acosmist. So acosmism is the view that whatever you see of the reality, whatever you see, it's basically a view consistent with effective field theory. So you might see that table is real, but table is not really real because it's made up of atoms, and atoms are not really real because they're made up of electrons, protons, neutrons. Electrons, protons, neutrons are also not really real if string theories. They're made up of strings. Even if they're not made up of strings, they can't still be real because they're quantum fields in space and time. But space and time is also not real because it's made up of information, and information has this Godelian problem, and it goes back to all a projection of consciousness. What is consciousness? Something that overcomes the Godelian limitation. And everything that you see after that is an approximation. Everything that you see after that is a limitation of that, or is rather, I would use that word approximation. Now, this is something I think where we have naturally come to from quantum gravity, and if you take problems, if you take the philosophy of mathematics theory, I mean, if you take Godel's theorem seriously. But this is not the only time we have come to these conclusions. It's very interesting that across world traditions, and this is something again I would love to discuss, across world traditions, from Eastern to Western traditions to Middle Eastern traditions, acosmism, I would say, is the predominant philosophy of almost all religions except maybe Jainism, or maybe few religions which were based on mythology, like few mythological elements of religion. At the end of it, it really reduces to acosmism, and I can discuss. That's a very interesting point of view, and most philosophers, if not all. So this is something again that I would say that and traditions like Spinoza and all, they all reduce, and there might be a reason why we humans come to acosmism, even from this is again interesting from an experiential point of view. People doing research on psychedelics have found that DMT can lead to experiences which can reproduce this sense of oneness, and people come to natural conclusions of acosmism. I think some research should be done with how meditative techniques affect this. Do they naturally produce DMT in our body, and does that lead to this acosmism? It doesn't deny the validity of that. It just produces a neurological basis for that. So I think this theory is quite widespread. For example, in Pakistan, from an Islamic point of view, acosmism was called Wahdatul Wujud. Next to us, from an Indian perspective, it was called Advait Vedanta. From a Chinese perspective, it was Taoism. From an Eastern Orthodoxy, it was what was it called?
Theosophism.
I forgot the name in Eastern
Theosophism.
Orthodoxy, but yeah.
Theosophism.
Theory. Yeah, the idea of you becoming one with reality. I forgot. No, I forgot.
There is one more question by Dr.
Well,
Pervez
it's not a
Udbay.
question, it's a clarification and a statement of my understanding, my position on this. I agree with you, Faizal, that everything doesn't have to lead to technology. And it would be very sterile if we said, oh, we look at a theory only because ultimately it'll produce some good for us. No, that is not the way to go. However, you can't, in my opinion, one should not investigate questions for which there is no reasonable way of getting to the solution. Instead, one should focus upon what are the issues that the application of science in certain situations brings. So, for example, now, Shahryar, you said, multiverses aren't detectable, but I think it is still good science because this was something that was postulated in the quantum theory of measurement. You make a measurement, and according to the multiverse theory, you create a universe at that point, which then propagates on and so forth. Those are not measurable. However, this is a valid way of trying to explain something that was puzzling. That was a puzzle that came from within science itself. Now, there's another way of answering that. And so, as Abdurrahman over here asked, he said, who needs to observe? And this is an answer that Steven Weinberg gave. He said, any system that has a sufficient number of degrees of freedom. Because that system will then evolve very quickly, and it'll cause the wave function to collapse. To collapse, but not in zero time. It'll take a finite amount of time. Anyway, I don't want to go into that. The point is that issues that arise from within science and which can be tackled within the framework that exists are ones that are worth then thinking about spending your life on. Mm-hmm. But if you want to figure out how many angels dance on the tip of a pin, well, you can do that. Will it get you anything? I'm not sure. Mm-hmm. So, worrying about whether our thinking is algorithmic or non-algorithmic, maybe if science brings us to a point where that becomes a genuine question, which then has a solution within the space that is available then I'll say, yes, that's good science. Otherwise...
Actually, Penrose bases his whole theory of consciousness on the algorithmicity of consciousness. So this has been an ongoing project
but just
for
because
few
Penrose
decades.
has done it doesn't make it, doesn't...
but still, lots of people followed.
I definitely would like to have a question, take on many things. So there are things I think where Professor Pei and me would completely agree is that everything does not have to be technology. But really, if you look at it, I mean, I'm a bit surprised by the comments on many world interpretation of quantum mechanics because there are many models of multiverse. There is the brain world model where you have extra brains in higher dimensions, and I think that is falsifiable, and that's a scientific theory. I actually worked on brain world models where I worked on the idea that a mini black hole produced in CERN could actually be used to detect these mini black holes. models. That got a lot of press anyway. There's some jokes to that too. So there are models of multiverse which are detectable. There's a very interesting model in which you take Wheeler-DeWitt approach. You third quantize the Wheeler-DeWitt and you produce an infinite number of things. Like each of the creation annihilation operators now don't produce particles, they produce universes. So there is a very well-defined model of multiverse based on that. One of my collaborators is working on possible implications of this in signatures. Like could even these models have detectability? There is one model of multiverse that I would strongly disagree with, and that is the many world interpretation. And I really think that this is not even good philosophy. This is just poetry. And this is bad poetry. Why? I don't think anybody disagrees with it. And my challenge is simple. See, anybody who professes some kind of belief in many world interpretation of quantum mechanics, I tell them a very simple thing. Let's do a thought experiment. All of us are happy to be alive, one version of us to be alive, and would be happy if one version of us is doubly rich. So let them sit with a friend of them. Two friends sit together, put all their money, and take a quantum particle in a superimposition of two states, collapse it. If it collapses to one state, one of the friend dies and the other friend gets all the money. And if it collapses to other state, another friend dies and the first friend gets all the money. Nobody will do this experiment. Why? Because nobody takes the very world interpretation of quantum mechanics seriously. I don't think this is good science. Copenhagen interpretation, yes, there is this approach. The approach that we just mentioned is the idea of environmental decoherence that Weinberg was a big fan of. But then we still have the problem of retrocausality, and we have these problems that environmental decoherence cannot measure. And the fact that we have just this year been able to produce interference patterns in time. How do you resolve that? I think the best way is, again, I see that there is this problem. And then they would say that, okay, maybe a measurement made in future. Either you take a view where you do not define the observer and just say that observer is there. And if you want to have any physical definition, I don't know why, but I seem to agree with Roger Penrose even in this one. He has actually also developed these objective collapse models, even though his models are not the only models. There are other people working on objective collapse models where you modify the Schrodinger's equation either by a stochastic term or by another term. And this term produces small deviations from quantum mechanics, but it causes a collapse of the wave function. Now, the third point is that if you can accept a solution to measurement theory, which has basically different approaches to measurement theory apart from the approaches like collapse models would not be even experimentally distinguishable. These are problems that come from within science. The idea that space-time breaks is a problem that comes from within science. Everybody in quantum gravity almost accepts it. People have published papers in Nature even in this year on this. I have hardly met anybody working on quantum gravity, serious quantum gravity, who doesn't accept it. In fact, I am the moderate guy here. I met Julian Barber in Oxford, who is one of the leading guys in quantum gravity, and he thinks time doesn't even exist at our scale. He thinks time, because he's a new Wheeler-DeWitt absolutist. And I told him, but we see time. He said, well, this might be an illusion produced by our consciousness. So I'm the moderate guy in quantum gravity who at least accepts space-time as an emergent reality. There are extremists out there, Wheeler-DeWitt extremists. I just gave you an example of Julian Barber, one of the leading guys who, at least Mollin says, is instrumental in the development of loop quantum gravity. If I remember, that's at least what Julian Barber himself told me. And he thinks time is not real. I don't even go down that extreme. I'm the moderate guy in quantum gravity. He thinks space and time is real. I'm not even addressing the problem of time. In problem of time, people come up and say time is unreal. I'm somebody who says time is real.
But people who use cyclical time, there are people who use 2 times instead of 1 time. I don't think that makes any sense at all.
Well, it actually, people use extra dimensions in string theory. You can come up and say, well, I don't like a theory, and that is fine. And I think we have undergone an evolution in science, and I will be honest here. We have 3 levels. One is technology. Science is only what technology is. And another is the level of phenomenology that experimentalists and nuclear physicists and people who are working on anything in flat space-time would agree on, that everything has to be, at least your theory has to be experimentally verifiable. But the very moment you go to when you quantize space and time, you lose this, I would say, luxury of having that. And then what are you left with? You're left with at least a theory which is consistent, because consistency is the bare requirement of reality, and then you come to the conclusion. And I think almost everyone has come to this conclusion.
Faizal, there are some
There might be
questions that
exceptions.
one should not ask. Like
Well,
what?
like
are
a single resolution of singularity.
Like, what is the purpose of life? Are you going to ever find a mathematical way of dealing with that?
Well,
You're never going to do that.
No. But we are addressing rather more simple questions right now, and I would say what I have addressed is physical, because do you want to resolve the singularity? Is general theory of relativity a UV complete theory? These are very.
I would like to
questions.
resolve the singularity if there's a purpose to it.
But why? It can't be experimentally detected.
No, it may not be experimentally detectable, but at least there's a theoretical basis for asking that question.
Okay, the theoretical basis is quantum gravity, and as soon as you try to develop any theory of quantum gravity, you take. Okay, let's put it really simply. You agree to canonical quantization and you agree to covariance, right? I would expect you agree to both of them. What happens if I canonically quantize general relativity? Time is a gauge parameter.
You get
What would happen?
non-renormalizability.
No, you not you get non-renormalizable only if you do perturbative quantum gravity. I'm not talking about perturbative quantum gravity. I am talking of the Wheeler-DeWitt approach. You take a full metric, not a fixed background and small perturbations. That's not proper quantum gravity. That's just perturbative quantum gravity that T. Hooke laid with. Now I'm talking of Wheeler-DeWitt approach. You take the metric, you make a 3 spatio-time temporal decomposition, and you apply the canonical quantization. You know what you get? You get a Schrödinger's.
Okay, I think this is getting too technical for most
No,
people
but,
over
but,
here.
but, no, no,
Let's-
but just a simple clarification. Your Schrödinger equation is x psi equal to 0. You know, Parvez, what is the implication? There is no time, and that's why people in quantum gravity who are extremists think there is no time. Time is a delusion. I don't go down that road. I actually think space-time is real.
Yes,
I
okay,
actually think
yes,
space-time
yes,
is
I think
real.
we can continue this discussion, and I think Sir Parvez would agree that our theories need to be complete, UV complete, and we need to formulate a theory of quantum gravity. That's why he also appreciates string theory as well. I think his main criticism was that your ideas about consciousness and algorithmicity.
That is not even my idea.
That's
That is
that was
idea.
I think that was what he was referring to as a bit far fetched.
Well,
But yes,
but that is the strongest part of the argument because that is by Godel. We can be wrong, but that's
Yes.
a mathematically.
But though
proven
that
idea.
enters into the realm of philosophy, right? It leaves the
That
realm
really
of science.
enters the realm, I would say, of mathematical philosophy, and that is more
Yes.
founded than physics.
Yes, so
You
there,
can't
there
deny-
can be I also have lots of questions. I can reach out to you via like email as
I
well.
would love that.
So
I would love that.
yeah,
Because to
especially
deny from-
Godel's
you see,
argument.
if you accept space-time not to be an emergent structure from information, then you are only left with Godel's paradox. You will have to reject Godel's theorem, and which can't be rejected. You can even reject. You can start from rejecting, physicality. You can say that the universe is absurd. This is more acceptable than to say that Godel's theorem is wrong, because Godel's theorem is demonstrated to be true.
Or
It's a
we can say
theorem
that
deep in
human
mathematics.
consciousness is algorithmic. We can also say that.
Well, you know what I did? I took the criticisms of randomness also into consideration. I said either human consciousness is non-algorithmic or it's inconsistent because of the Godelian limitation. Then I took this argument and said, because the same argument would apply to axiomatic structure of the reality. So either the axiomatic structure of reality is inconsistent and universe is inconsistent, which is not conceivable, or there is a consciousness as a non-algorithmic process behind it. It is a very simple argument which follows directly from Penrose-Lucas.
Okay, great. So it was a wonderful session. The audience and all of us really appreciate your time, the time that you gave us. Really fruitful and wide-ranging discussion. So thank you very much. Let's give a big hand to Dr. Mir Faizal, and hope to see you again next time as well, in the future as well.
Pleasure. It
So
was a
thank you very
pleasure.
much for giving us your time. Thank you.